to start building some machine learning model for the company. So this is going to be deployed on a full stack application, but using the company's data, it's going to be stored in DynamoDB, and it's going to have the partitioning architecture. That's all that's doing. And then we're going to extract it and transform it and load it using Glue. And then we're going to perform feature engineering. We're going to split it, train the algorithm, evaluate it, and then deploy it once we're ready. So that's exactly what we're building today. All right, so first we're going to look at our data. So we're going to query DynamoDB. So essentially we're going to select the SK column from the table and where the PK is VIPS. So we'll run this query and we'll see that we have some data issues. So remember that I told you that the PK and SK combination must be unique. But in this case, since 14 is not 2014, then we're good to go. Well, if I were to put a 2014 there and remove that duplicate, we would be good to go, right? So we essentially want to add a 20 to each of these numbers with only 2 digits and then remove them because that's not allowed. So that's the first issue with this data. And we have a lot more on the machine learning section. And now we're going to run another query on this column, book value per share growth, where the PK is MDLZ. And that's just going to show you some issues with the data again. So the parentheses could mean that it's negative. So accountants typically put their negatives in a parentheses. So right now that's a string. We're going to convert it to a negative and remove the parentheses. These are very simple transformations. Now in the real world, you would use Glue to continuously extract, transform, load from this database and make a lot of transformations and continuously upload to the machine learning model. So we would continuously train with new data that's coming in. So we'll select these columns from the table and where the PK is PG. And then this shows that price variance problem that I showed in the slides. So we're going to combine that into one price variance. So right now you guys cannot do anything on this section, but I will go through it myself. So this is a Glue notebook, and this is how we are going to transform our data. So first is the imports, and we are going to set the number of workers to 5, and then import a bunch of imports that we're going to need. Next, we'll run this the Spark section. So we have to create the Spark session, and we'll be good to go and start transforming the data. So I've run that. Okay, now the more important part. All right, so the source dynamic frame, we're going to create a dynamic frame from DynamoDB, and the table name is table 5, and then we'll define our throughput read percent, which we don't have to know, and the DynamoDB splits. So essentially, I've extracted from DynamoDB. That's all I've done here. Now here comes the transformations. So we're going to make it to a data frame. Source dynamic frame .2df, just to a Spark data frame, and we are going to rename columns PK to stock symbol, SK to year. Very simple. It's key to remember that these transformations are really simple because of demonstration purposes, but Glue is meant for huge data, and you can make pipelines to continuously transform and load to a model. So in the real world, we cannot make a model and then simply forget about it. It will continuously get worse performance if there's new patterns. So here, I'm going to make the first transformation. So if the year column has a length of 2, and we are going to append a 20 at it. So 14 now becomes 2014. That's all that means. And then we want to drop these because that's not allowed, one in machine learning and in DynamoDB. And now we're going to modify the columns. So we've listed the columns to modify, and we are now going to remove the percent sign because there is a percent sign in the price variance values. So that's all we're doing. We take out the percent sign. These are very, very simple transformations. So yeah, you can see here, the percent sign becomes nothing using regex. That's very simple. And then we'll do it again with price variance columns again, and we're going to do another transformation. We're going to convert it to a double, and then we're going to apply that function we saw and essentially get the new price variance column. So now we have no more missing values, and we have one price variance column. And then we're going to drop the rest of those price variance columns here. We're going to drop this because we don't need it anymore. So now we have a new price variance column, and it's like this. So now we're going to modify another column, book value per share growth. And we're going to take out those parentheses. Remember, we had parentheses, and we wanted to convert it to a negative. So where we find parentheses, right here, we're going to remove those parentheses and then cast it as a float and then multiply by -1. The reason is, it's because it's a negative. So it's a parenthesis value, we remove it, we multiply by -1, and we're good to go. And then otherwise, we just convert to a float. We'll convert back to a dynamic frame. And now, I'm not going to go through this too much, but essentially this is how we're going to write to, we're defining a function on how to write to Amazon S3. So essentially we pass in the path and then we write to S3. That's all I can go into today. So we're going to process for each year. So for what this means is, as we process, put in a year into this function, it's going to split the code or the files separately. So 2014 will have its own file, 2015 its own file, 2016 its own file, and so on. And then since it outputs a bad name, we're just going to rename it. So that's all this does. I'll go more in depth for the machine learning because this is not really what we're trying to do. So I'll wait for these to run. And I'll run this one more time, run this. So essentially this is just using the function above to rename the columns, and we process all the years. And then we'll commit the job once we're done. Any questions so far? Now, it is key to know that if I were to increase the number of workers by a lot, then I can process this thing very fast. But since I'm not going to, do that for such a small transformation, it's going to run slower. But it's very powerful. We've just extracted from S3, or excuse me, DynamoDB. We've transformed it and loaded it to DynamoDB in a few lines of code. So as you can see, we've applied the rename function. So before it was this name, and then we've renamed it to 2014 Financial Data Debug. So yeah. And then we'll commit the job to end the job. All right, so now we are on the Kaggle notebook. So you guys can follow along as with me as well. So first we have the imports. And now we have to extract the data from S3. So we define our URL, and we get the URL, and then we have some error handling, and then we're going to save the temporary file, and we're going to read that CSV from the temporary file name, and then we'll return it. So now what this is doing is that we're going to apply the function load financial year to the year 2014, and df1 will have only years 2014 data in it. And we pass the year in because we want to modify the year here, as you can see. So 2014 financial data dub is now, that's our 2014 data. So now we have a bunch of data frames with separate years. We'll import warnings because if we were to look at a data frame, just like DF like that, and look at it, then we could encounter some warnings because there's missing values. So we don't want that. So now we're on feature engineering. So first we're going to drop the stock symbol because we don't, and the sector, because we don't want any influence from the sector. So I could say that the technology sector is probably a buy in a stock, so you don't want to skew our data in that way. We're also going to make class as an object. So simple transformations. Now we're going to replace the outliers with a median. So what that means is it's just interquartile range. We do this formula exactly as I showed in the slides. Q1 is the 25th percentile and Q3 is 75%. We subtract the two, we create a lower bound and an upper bound, and then we take the outliers, and it's just going to be like a true or false values. So if the value is true for that value, then that means it's an outlier. And if it's true, we're going to column dot median, which is just impute the median, and then we're going to return the column. And we'll do this for every single data frame, which is df1, df2, blah blah blah. All right, so now we're going to drop missing columns. So if a column has a lot of missing values, we'll set a threshold to 70% by default, and we'll set it here too, it doesn't really matter. Then we're going to compute the percent of the column that's missing. So the data is null, and then we take the mean of it and multiply by 100 to get a percent, and then we'll drop those percents. If and only if that is greater than the threshold. And we'll drop them here. And then we'll print it. So simply put, we have now dropped 2 columns. And now we're going to load the imputer, which is KNN imputer, and we'll set the number of neighbors to 20, the weight as distance, and the metric, and it's the exact same as I did in the slides. So now we're going to apply the KNN imputer. And what this will do is apply it to the data frame, df1, and we'll do it for df2 and so on. And then we'll save it to another data frame because it returns as a numpy array. So we'll make this data frame, the df1 clean, into a data frame, and then we maintain our columns. So this will take a little while because it's running through the whole data set, which is about 26 rows of data. It's not a lot, but it'll still take a little bit of time. And then from there, we will combine all of our data frames. So we have df1 clean, df2 clean, df3 clean, and so on. And we'll combine them into one, and we'll print if there's any null values. Next, the data drop. So what that means is we take this variable here, and we'll drop the columns of class. So X is our independent variables, which means it's just everything except for the label. And a label is our class. So class is either 0 or 1, essentially. So, and then Y will be our class value. And then we'll perform our splitting. So first we'll split the training and testing to 20%, and that's done with this code, and random save means we retain the split. And then we'll do it again to make a validation set. Then we'll perform hyperparameter tuning, and of course we're going to use grid search. There's many other ways, but we'll use grid search because we have a small amount of data, so it's okay. So we'll define a parameter grid, the number of estimators, which is just the number of trees, and so on. And just to see if we have any null values, we do not, they're all 0, so we're all good to go. So now we are ready to initialize our model, random forest classifier, which is random forest. We'll initialize it to RF model, and then it will have it as Gini impurity, random state 42. And then we'll perform the grid search using the grid search library. We'll pass in the random forest model, the parameter grid, the amount of k folds, CV is equal to 3. We'll have it to verbose equal to 1, which is just showing it'll tell you feedback essentially. And then the number of jobs is -1 to use the maximum computation. And then we'll save the best model. So we've applied the grid search, and we'll save the best model into 1. So we've applied the grid search with a bunch of different hyperparameters, and we'll save it into the best model because we want, the best hyperparameters. And then we'll make the predictions on the validation set, and then we'll evaluate. So we'll print our precision score and our recall score. So essentially, we've applied our hyperparameter tuning, and we'll show the precision and recall score. Any questions so far? All right, so now we've ran the model, and now our random forest classifier after hyperparameter tuning is 97.24. Now, if I didn't do this, it was roughly, I believe, 60% or 70%. So hyperparameter tuning is very key here. So the precision is 97%, which is very high. The recall is 97%. And now we're going to evaluate our model once more. So instead of evaluating it on the validation, as we did here, we are now going to evaluate it on the test. So now our test precision is 97.43 and a recall of 97.61. So that's all we've done. We print out the precision and recall. And now we'll make an ROC. I'm not going to go fully details on how it's just like, X label, Y label, sexual. It's pretty easy to understand. But yeah. So now we've printed our ROC. Our ROC curve is this blue line, obviously, and the AUC is 0.99. So our area under the curve is very, very high, which is good. Now we're going to check if we're not overfitting here. That could be an issue. Now, if you were to over hyperparameter tune this thing, since this thing, the data is very easy, honestly. We're not classifying stocks as a buy or sell in real time. We're only doing it at the end of the year, so it's pretty simple. So what we have to do is check if we're not over hyperparameter tuning this thing. We have very high accuracy for random forest, which is good, but since from the hyperparameters we can really bump these up, it's key to understand that if this were 100, for example, the training was 100, and the validation was 95 or 97 or anything like that, if it's a little lower, it shows that there's something a little off. But since it's a very small difference, then we're good to go. So essentially, when I was first making this thing, the training accuracy was 100 because it's very simple data and you can easily overfit it with hyperparameter tuning. Then you could change the hyperparameters, and then now you can now lower the score, which makes more sense. You don't want a training of very high and then a validation of much lower, which would be kind of overfitting. And that's all for today.